The deep sea is huge, dark, and almost unbearably cold. Giants abound as well. We initially travel through the epipelagic zone as we start our descent into the ocean's depths. Almost all marine life can be found here thanks to the sun's piercing intensity. Animals abound in this area and are colorful. The mesopelagic zone, sometimes called the ocean twilight zone, is the next stop on our journey. Here, the light is incredibly faint, making photosynthesis impossible. All light is lost below 1,000 meters, and we enter the midnight or bathypelagic zone. The only illumination down here is the blazing bioluminescence from squid skin or anglerfish lures. Here, there is intense pressure and surprisingly low temperatures. The ocean, though, is even deeper. With a pressure that is 600 times greater than our planet's atmosphere, the abyssopelagic zone can be found at depths of up to 6,000 meters. The abyssal realm, which makes up around 60% of the planet's surface at 300 million square kilometers, is regarded as the planet's single greatest environment for life. However, the ocean's depths don't end there. The deepest part of the ocean is called the hadopelagic. It is found in long, narrow topographic V-shaped ditches at a depth of between 6,000 and 11,000 meters. The Mariana Trench is the deepest part of this ever found. And against all odds, life persists in these ominous depths, where the animals have evolved into being incredibly bizarre, ranging from the ghostly to the scary to the utterly enormous. Examples of deep-water gigantism include the huge Japanese spider crab, large red jellyfish, king of herrings oarfish, giant squid, and Greenland sharks. Why do these organisms grow so large in such frigid and murky waters? Before we proceed, kindly return the favor and give this video a thumbs up, subscribe, and activate the bell notification feature to stay up to speed with new video publications. Food becomes scarce in the water at depths below 400 meters, and when sunshine diminishes, photosynthetic algae and plankton also vanish. The majority of them must instead rely on debris that falls from shallower seas, a phenomenon known as marine snow. Dead plankton, fecal pellets, and bits of decaying bodies that fall to the sea floor as fine particles make up the majority of marine snow. Some species are wholly and exclusively dependent on marine snow. The vampire squid, for instance, has a particular adaptation that makes it easier for them to capture and consume the drop particles. To catch any drifts that may pass them in their 900-meter deep home, two long filaments emerge from their bodies. The foundation of all deep-sea life is marine snow. However, it can't hold a lot of biomass. The food web is stressed and there are few species in the depths. Many species rely on consuming those who do, rather than directly eating marine snow. Predation pressure is therefore at an all-time high. A large target on its back is any little fish, crab, or cephalopod from larger predators. In order to change from being a prey animal to a top predator, it became evolutionarily advantageous for animals to get rid of the target on their back. A live giant squid was captured on camera in its natural habitat in the Twilight Zone in 2004 at a depth of roughly 1,000 meters. While we may not know much about this enigmatic creature, we do know that they are enormous. The longest one ever discovered was 13 meters long and 275 kilograms in weight. Considering that the bulk of squid are no longer than 60 centimeters long, these giants are quite remarkable. The enormous squid, however, is not the biggest species of deep-sea squid. The largest squid in the world is known as the colossal squid or Antarctic squid. They only measure 10 meters less in length than the giant squid but weigh between 500 and 700 kilograms. Such a large creature makes it simple to see it as an aggressive predator, darting through the water, capturing prey, and dominating foes. The squid, however, tells us that deep-sea predators are not always the dominant predatory force as we might assume. They have an extraordinarily slow metabolism as a result of their huge size. Kleber's rule and Bergmann's rule appear to be the two general rules that govern this expansion. The enormous squid extends Kleber's rule even further. According to Kleber's rule, larger animals are typically more productive. For instance, a cat, whose mass is 100 times greater than that of a mouse, has a roughly 32-fold higher metabolism than a mouse. Kleber's law is a result of the physics and geometry of animal circulatory systems, just like many other biological allometric rules. Additionally, the surface area to volume ratio and the fractal nature of blood veins play a significant role. Huge creatures that live in the ocean's depths depend on food that falls from the shallow sea, and because food is frequently in short supply, they have every reason to grow larger by becoming more efficient. According to one study, colossal squid only need 0.03 kilogram of food per day and only burn 45 calories per day due to their extremely low metabolic rate. A 500 kilogram colossal squid could survive on one adult toothfish for about 200 days. Their energy needs are 300 to 600 times lower than those of other top predators in the southern seas of comparable size. This suggests that they live at a particularly leisurely pace. Contrary to what we may think, it doesn't engage in epic hunts for prey. Instead, it waits for its prey to accidentally approach before entangling it with a hook on its arms and tentacles. This opportunistic way of life makes a lot of sense given that visual predation will be at best impossible in such deep water due to extremely low visibility. The colossal squid possesses the widest eye of any animal in the world, measuring up to 30 centimeters in width, but scientists think that rather of using it to catch prey, it uses it to identify and avoid predators. One of the main factors driving deep water animals to grow big and have such a slow metabolism is the lack of food and the need to avoid predators. However, they are not the only pressures. The cold, deep water itself drives gigantism. According to Bergmann's law, a person's physical size generally decreases when their body temperature rises. Smaller populations and species are found in warmer regions, while larger populations and species are found in colder habitats. However, this is more of a trend than a universal truth. Warm-blooded creatures experience this because their larger size results in a smaller surface area in contact with the environment relative to their volume. However, this is linked to cell division and a longer lifespan in aquatic creatures. Does this pattern also apply to ecotherms, such as the deep-water squids, crabs, and isopods? It is a surprising field of research, but it is undeniable that some ecotherm animals grow larger in colder climates. This can be observed in the Arctic zone where single-celled creatures, marine sponges, and worms can grow to enormous sizes. The predominant explanation for this phenomenon is that cooler water carried more oxygen, allowing aquatic organisms to develop such huge body sizes. Not to mention the Greenland shark, one of the biggest sharks on Earth and the biggest fish in the Arctic water, 7 meters long and up to 1,400 can weight. It inhabits an almost 2,000-meter deep environment with a temperature range of -2 to 7 degrees Celsius. It is the only shark that can survive the Arctic's icy seas all year round. The shark is made extremely old and enormous by the extreme cold climate. And now let us hear from you in the comment section below. Keep in mind that more videos will be up soon. So be sure to like, subscribe, and hit that notification bell in order to stay up to date with new video alerts. Also, sharing indicates you want to see our content reach a wider audience. Thanks for watching. See you in the next video.